Hello everyone. In this section, we call it thin wall tubes having close cross sections. This section actually talking about the application for some kind of lightweight structure. For example, in engineering application, thin wall structure usually used for aircraft, just like this one. You see the cross section of aircraft. It's very similar to what we mentioned over here, a closed closed cross section with a very thin wall, and the shape will be pretty complex, and the thickness of the wall won't be totally equal. Similar structure can be seen in like HSR trend structure, just like this one. Okay, you can see the shape is like a closed structure. Okay, and the bottom one is similar. Okay, these are the wheel. Okay, so this would be one of the application. Okay, also you can see car body, rocket is like this one, bicycle frame. For general shape of bicycle frame, it looks like a triangle. Okay, however, if you cut the frame itself, just here or here, you will see similar shape like a hollow tube with a pretty complex geometry. Also, the thickness of each place may have small difference compared with each other. Okay, so that's the reason we need to study thin wall tube, especially under torsion condition. The torsion condition usually may apply to such kind of engineering structure. For example, like what we have mentioned in this sentence. Okay, so how to deal with this kind of structure? We try to make a schematic plot with pretty random shape, and notice that the thickness at different places, different location of the tube uh, indicators is defined as T, and it may not be constant along the circumference. Okay, so that's the initial condition. And then if we apply a torque on this tube, we can cut the cross section over here. And in order to study the internal stress or similar load inside the structure, we try to cut these very thin slides with the thickness of dx, and along the tube, it's just like a ring. Okay, we cut a part of that with a length of s and make a free body diagram just like this one. Okay, so for this free body diagram, we just check 2 points A and B. This point is A with the thickness TA, and point B with the thickness of TB. Okay, and notice that TA and TB are not the same with each other, so that indicate we can have different thickness. Also, the shear stress on this plane, we call the shear stress at A would be tau A. Okay, so TA tau A, TB with tau B. Okay, so for these two cases, the tau A, although these shear stress and this shear stress, we use a different size of arrow to indicate their magnitude may not be the same. But don't worry about this. We assume the shear stress from the top to the bottom are identical. Similar things happens here from top to the bottom, from the outer surface to the inner surface. Through the thickness, the shear stress should be equal. These are the this is the assumption for the following derivation. The reason we need to mention that because in previous sections we know that the shear stress of the structure under torsional condition, we assume we know that their distribution is linear proportional to your radius. So if you try to find or calculate the shear stress from here to here, usually they should have linear distribution the magnitude may not be exactly the same. They usually gradually increase from inner surface to the outer surface. But here, notice that we assume this is a thin wall structure. Usually, thin wall structure means, for thin wall structure, the difference of, because we assume that is thin wall. So the thickness, no matter the TA or TB, are so thin that the stress within that thickness should not have significant change, since you don't have sufficient distance to increase or decrease. Okay, so in order to simplify this derivation, just to simplify, okay, they should be uniform. So that's what we do. We give an assumption here. The shear stress over here, okay, shear stress is uniform distributed across the thickness of the tube. The main reason to make this assumption is coming from thin wall structure. Okay, so that's the main reason we can give this assumption. So next one, if you have uniform shear stress here, same as here, the resultant shear force along the surface at this place and this place, which plane? This plane and this plane. So the resultant shear force at here, we call it DFA. This is DFB. Each of them are defined over here. DFA equals to shear stress tau A times the area, TA dx. TA dx, that's the rectangle at this side, and this is another side. We got another another force, dF, called dFB. Due to equilibrium, the shear force at one side, it should be equal to the other side in order to get balance along this x-axis. So since these two forces should be equal, then we get an equal between these. We have an equation between this term and this term. Okay, next one, we get this relation. Since we can take the dx, we can remove the dx on both sides, we finally get a result. Tau A times TA equals to tau B times TB. So if you try to extend this concept from this element to the nearby element, then go to the next one, surrounded by the ring to the end, back to the original one, you'll find that no matter which place, the shear force at one side should be equal to the other side. Finally, it's equal to everywhere around the tube. Then we say they should be constant because they are equal to each other. And these magnitude, or these product of tau A, tau and T, this product Q is called shear flow. And the reason we call it shear flow will be discussed in the next slides. Here is the definition of shear flow. Okay, as we mentioned in the previous slide, the Q value is the product. The Q value is called shear flow, and it's the product of average longitudinal shear stress tau times the thickness T of the tube. Okay, that's the basic definition. But notice that the shear flow, why we call it flow? Because it's the same at each point of the tube. And this kind of feature, okay, is very similar to water flow rate inside a channel. For example, the tube around the thickness or the geometry around a tube, you may have different width with different stress on each point. But if you have a constant value, it's just very similar to the water flow inside a channel. So if your flow rate are along a closed channel, closed loop channel, okay? So the beginning to the end should be linked together, then you will find that no matter which place, if your width times your velocity equals to q, then if you have larger width, your velocity will be slow, and your width is small or narrow, then your velocity will be fast. But no matter which kind of combination, the product should be constant because your water flow rate, your volume, never decrease or never disappear, no matter in which kind of condition. So let's give you a very similar phenomenon or similar condition as what we have in our shear stress or shear flow condition over here. Then, based on this concept in the next, we try to see what kind of definition for Q over here, how to derive that in other way. So here is the A, dA. What is the meaning of dA? Which means TdS. TdS is the area over here. Okay, let's mark this place. This area. Okay, and the width of that is ds, the thickness T. Okay, then this is dA. Let's give this one dA, and the force on it can be derived as tau times dA. Tau is the shear stress over here, and this dA equals to TdS, and then we take these two value, two factor together, the product tau times tau average times T equals Q. Okay, then based on this result equals to dF, we try to take the Q on one side, the other side will be dF over ds. In this equation, we know that shear flow, which is constant over the cross-sectional area, okay, which is constant at everywhere along the tube, okay, along the cross-section of the tube, is or can be defined as the force dF per unit length ds. Notice that ds is the path length, the length of the tube, a portion of that, so along the tube's cross-section. So that is the definition for Q in this formula. Okay, and next figure here, we find that there's one interesting thing is since the shear stress can be found in this direction, so you also have the other direction, and these four there are three remaining shear stress component together with this one, so you always have four. And if you consider the free stress boundary, the bottom of that or the top of that, then you will find that there is no shear stress in this direction or this direction. So that means on the top of the surface, if there is no stress on that, that would be a stress-free boundary. Then the shear stress in this direction or this direction should be zero. That means inside the material there's no vertical or so-called transverse shear stress on this side, or the other sides. Okay, so that's another things we like to remind. Okay, so no shear stress on the top. Then you won't have transverse shear stress on all the surface inside the element. Okay. Then next one. After we define shear stress, shear stress, shear flow, and everything and their relation. Next one, we'd like to really calculate the average shear stress inside the tube, okay, or along the cross section of the tube. How to derive this one? we try to link this one together with the torque. How to link that? First of all, we select one element. Okay, you can say dA. Within the parenthesis, this one is dA. Just like dA over here. And then, how to derive that? It's TDS. Okay, this gray area represents TDS. We multiply this to, or times this to our shear stress, we get a shear force dF on that surface. Then if you want to get the resultant torque, you first need to derive a little torque from one differential element. So dF times your arm is h. Okay, O is here. Where is O? O is the centroid of this random shape or random cross-section geometry. So the distance from this point to our center or our original is O. We call it H. This is the arm. Okay. Then next one, we multiply dF into here, we get the whole information. Then in the next one, we not only consider this differential element, we also need to add all the shear force or the torque along the boundary. So we use a linear integral, line integral from one end along the circumference back to the original point, initial point. So once we achieve these points, next one, we try to consider this part. This production represents our Q, and this is a constant. Since the shear stress itself or the T itself may not be constant along the circumference, along the circumference, but don't worry about that. The production is a constant, so we take both of them outside the integral. The remaining part would be HDS. Okay, HDS means what? Just try to see this blue, little blue rectangular. H means the height, and this is the base. The production between them will be the area of triangle times 2. Okay, so this one represents the area of that times 2. Okay, so once we okay, this means this one 2DAM. What's the meaning of AM? Means mean area. This one. Okay, the area with the boundary along the middle of the tube. Okay, this is a very special area actually. We never see that in previous chapter anyway, but here we need that. Next one, how to derive the following contents. The integral along the circumference represent the AM times 2 because that's a triangle. The production represent the twice the area of the triangle times 2. So that's the reason we have 2 here. Then AM is the integral of this one times 2. Then the other one will be our Q over here. So overall, our tau average shear stress, equals to T over 2AM times T. Then next one, if you want to see our Q, you can take this T to the other side. T over 2AM equals to your shear flow. That's the way we calculate all the parameter in these slides. For example 5.11, in this example, we'd like to calculate the average shear stress in this tube, thin wall tube. This tube is has a very simple structure. It actually, you can think that this is a very typical thin wall circular tube. Okay, so it has a mean radius Rm and thickness T, subject to a torque T, capital T. All right. So mean radius, thickness, and torque. Then we'd like to know relative angle of twist. Okay, angle of twist for this tube with the length L. So first of all, you need to get average shear stress first. For this case, our AM in the equation can be simply derived by pi Rm squared. Okay, this one you can derive its AM. And then substitute to our equation, our average shear stress is given as this one. Okay. Next one, we check the validity of this result by applying the torsion formula, which means you still can use the traditional equation to check if this equation is valid or not, is good or not. Okay, so in this case, we use the previous solution. First of all, we need to derive J first. J equals to pi over 2 times RO with power of 2 force and minus Ri with 2 power of force as well. So this result actually can be divided, decomposed into two parts. This is the one part, this is the other, and this part can be divided into another two parts. Okay, as we know, Rm and T, especially T is very small, so we need to consider how to derive Ro and Rai by Rm and T. It says if Rm very similar to Ro or similar to Ri. The reason we have this assumption and T equals to Ro minus Ri, then in the previous equation, the J will be equal to pi over 2. This one is Ro squared plus Ri squared. Since we assume they are similar because of thin wall, this assumption, very important one, comes from thin wall structure. Because they are thin, so the inner and outer radius are similar. That's the reason we have this one. But if you want to see the T, it's coming from the last one. So plus you get 2Rm squared, 2Rm, and T is Ro minus Ri. That's the reason we have this equation. The final one will be here. Of course, J is nearly equal to this one. It's not really equal, it's nearly equal. Then once we substitute this into T rho over J, our average shear stress will be this one. Of course, average shear stress corresponding to Rm means the middle of the thickness. We take this one as an average value. So finally, we get the result like this, and we find that it agrees well with our previous results. And this one is the way we derive angle of twist. This equation, please try to keep this in mind and know how to derive this. Phi equals to TL over 4 am squared times G, and the linear integral, line integral will be ds over t. ds is the integration of the length along the circumference, and t is what? The t over here is the thickness of the tube at different place. So the integral represents the length. This total integral actually, it says you can take the t out if the t is equal. If t is not equal for everywhere, you still need to keep that inside the integral. But this ds means the length around the center line boundary. which is 2 pi rm. Substitute into that, the final result will be this one. Okay, this is the final result for this. And notice that this one, if you want to calculate the angle of twist for any closed loop thin wall structure, then this would be important equation. Here we have another tube made by bronze and has a rectangular cross section, and this is the cross section like this. We apply 2 torque at C and D. If it's subject to 2 torque, we like to calculate the average shear stress at point B and A. A and B is here, okay, over here. So that's the target we'd like to see, and the tube is fixed at this point. So first of all, if you want to calculate the average shear stress at A and B, first of all, you need to know the internal torque at that place. That is the free body diagram we'd like to use over here. Within this free body diagram, you will see that there's a torque here, the value balanced by 60 and 25. You can get a torque over here is around 35 at along this surface, along this place. And the calculation of this part, we're starting from AM. Okay, so this 35 is derived by free body diagram. Next one, in order to derive the average stress, there's another important factor you'd like to see is AM. What is AM? The mean area. This is the one, mean area. Okay, we need this area. So it's along the middle of each wall. Over here, just try to see this thin dashed line, and the area inside that is the AM. So we get this width and height. The production of that would be 0.002 meter square. Okay. After that, we try to see the location of A. This is the, for A, it's along the vertical line. So the TA here would be 5 meter. So this 5 meter comes from this place. Next one, we substitute the TA into the equation here, like this place. The torque is 35, AM will be 0.002. Okay, then we get this stress. Next one, we goes to the point B. Point B is around here. Okay, so the width of that, or thickness of that, will be 3 meter. 3 meter, we substitute into here, we get pretty large stress at B, 2.92 megapascal. So here we successfully derive the shear stress, average shear stress at point B. Next one, if you want to derive the angle of twist, okay, you need this summation. Why we need that? Because along the circumference of the tube, the top and bottom has one thickness. The right hand side and left hand side, the wall at there has another width. One is 3 millimeter, the other is 5 millimeter. So that's the reason the initial factor in over here, actually we just substitute the value we have in previous slides. AM, G, T, L. Don't worry about anything around this. But next one, the twist angle of twist at that place, one area is 35, the other area, okay, let me see. This one corresponding to this area. Okay, everybody is here. The next one, you will have this one, all right? And the thickness here, since one is 5, the other is 3, and one side, left and right, top and bottom, both of them, you need to add them together to get one twisting angle of twist for this length. Okay. Next one, this term comes from the 35 Newton part. 35 times 1.5 with the factor shows here. Similar things happens over here. This is the linear integral for ds over t, just like this one. Okay, so you got the length divided by the thickness t. Similar things over here. Vertical one would be 5, horizontal one would be 3, and both of them have 2 sides. So that's the reason we have all these boundary and results. So finally we get this angle and radian, just like this result.